All right, so then let's consider this case where we have W, which is spanned by two vectors x1 and x2. x1 is the column vector 3, 6, 0, and x2 is the column vector 1, 2, 2. And again, we note that initially these two vectors are not orthogonal to each other. So this basis, so the set x1, x2, although it spans this subset, and it's linearly independent, so we have a basis for this subspace. These two vectors are not orthogonal, so this is not an orthogonal basis. And we've seen why orthogonal bases are particularly nice. So let's think about how I could find an orthogonal basis for this subspace W. And so the picture that we have over here on the left is, here is the vector x1, which was 3, 6, 0. So we're going 3 units in the x1 direction, 6 units in the x2 direction, and no units in the x3 direction. And my second vector, x2, that is sitting right here. So this is the vector which is going 1 unit on the x1 direction, 2 units in the x2 direction, and then 2 units up. And so this vector x2 and x1, the angle between them is not a right angle. So these two vectors are not orthogonal to each other, but they span this subspace W. So what I would like to find is a second, or two vectors, v1 and v2, that are orthogonal to each other and span this vector, this subspace W. So we can start this process by saying, let's identify two vectors, v1 and v2, that span the same space, subspace W, but now when I take the inner product of v1 with v2, we should get 0, so that those two vectors are orthogonal to each other. So let's just start with v1 being x1. So I'm going to set, in this case, v1 is just going to be this vector 3, 6, 0. So that's this vector that is sketched in blue. We don't need to change that. But what I do want to find now is, what is this vector v2? x2 is not going to do the trick if my first vector v1 is equal to x1. This is not orthogonal to that. So let me first describe the game plan, and then we can do the calculations. So what I'm going to do is take this vector x2, which is this vector that I'm drawing right here in the plane in green, and I'm going to project this vector onto the line which is generated, which is spanned by the first basis vector v1. So here I'm going to project this down, and we're going to get a vector that is right here, this vector p. And then what I can do is find the component which is orthogonal to v1. That's what we're going to call v2. And this is going to be the second basis vector, which is going to give me orthogonal basis. So the first vector is v1. And then what I'm going to do is going to find the component of x2, which is orthogonal to v1. And that's this vector v2 that I've drawn in blue. And now these two vectors are going to span that subspace W, and they're going to be perpendicular to each other. So let's first find this vector that I'm calling P by finding the orthogonal projection of x2 onto v1. So to do so, it's the same operation we've been working with, finding these orthogonal projections. Except now this vector x2, I'm finding its projection just onto this line which goes through the vector v1. So this vector p is going to be some scalar multiple of the vector v1, and we can find out what that scalar is using this shortcut, which says we take x2 inner product with v1, and we divide that by the inner product of v1 with itself. And so all of these calculations that I'm showing, these are performed in the Google Colab notebook, which is linked in the description to this video, so you can verify these. I encourage you to do these by hand for sure, so that you can get exact answers, and then you can check your answer using Python, using Google Colab. So this x2 inner product with v1, that gives me 15, and v1 inner product with v1, that gives me 45. And remember, our v1, that's just this vector right here. We get the 9 plus the 36, and that's where the 45 comes from. So this is the scalar that we multiply by our first basis vector, which was 3, 6, 0, to give us the vector 1, 2, 0. So this is this vector p that we've drawn right here. And this is not the second basis vector that I want to pick because this vector is parallel to v1. So these two vectors do not span w. But what I can do now that I've got this orthogonal projection is I can figure out what the complement to that orthogonal projection is. And this complement is going to be perpendicular. It's going to be orthogonal to p. So to find that complement, we take, which we call this vector z, we're going to take our initial vector x2, which was 1, 2, 2, and now we subtract the orthogonal projection p, which we found to be 1, 2, 0. And the result is vector z is 0, 0, 2. So that's this vector that goes up right on this x3 axis because it has no direction in the x1 or x2 directions. So this vector z is orthogonal to the first vector in our basis. But we want to check to make sure that this vector z sits in our subspace w. And so since z is equal to x2 plus some scalar multiple of x1, that means it has to sit in the space which is spanned by these two vectors. So now I know that z is in the subspace spanned by w. I know that z is orthogonal to x1, and so the set that consists of x1 and z consists of two elements that are linearly independent, so therefore they span w as well. So now I've got a basis for w that is v1z, so the first vector is 3, 6, 0. I haven't changed that one, but now I tweak this second vector to find an orthogonal complement, which was 0, 0, 2, and now these two vectors span w, and they are orthogonal to each other. And so while this example is fresh on your mind in this video, on the next slide, I want to generalize this process, what's called the Gram-Schmidt process for finding orthogonal bases. Okay, so in general, if we have a basis for some subspace W of Rn that consists of p different vectors, x1, x2, up to xp. So each of these vectors is in Rn. And we would like to take this basis, which is most likely not orthogonal, and generate an orthogonal basis for this subspace W, so that working with projections and doing approximations, these calculations are going to be simplified considerably if we instead work with an orthogonal basis. So as we worked through the previous example, we first pick our first vector to be x1. And then I want to make sure that the next vector that I pick is orthogonal to the first vector. And this is exactly what we did on the previous example. Namely, I would find the orthogonal complement of x2 to the first basis vector v1. And we find that by calculating the appropriate weight, finding the orthogonal projection onto v1, subtracting that from x2 to get the orthogonal complement to v1. So this is my next basis vector v2. And then to find v3, we just continue this process, except now we're going to find the orthogonal complement to the subspace that's spanned by our first two basis vectors. So this means I'm going to find a vector v3 which is orthogonal to both v1 and v2, but still sits in the subspace W. So since v3 is a linear combination of x3, v1, and v2, it sits in the subspace spanned by these three vectors, but it is going to also be orthogonal to the previous two vectors. So now this basis v1, v2, v3 is an orthogonal basis that spans the same subspace as x1, x2, and x3. And we just keep this process going until we have found the last vector vp that's going to be in the orthogonal complement to the subspace, which is spanned by all of the previous vectors. So that's going to be p minus 1 of them. And now the collection of all of these vectors, v1 up to vp, they all sit in the same subspace W. They're all orthogonal to each other, so they are going to form an orthogonal basis for the subspace W, v1, v2, all the way up to vp. And if we stopped anywhere along this process, moreover, we see that the span of x1, x2 up to xk, so if I stopped short of going all the way out to the pth vector, that the first k vectors that we get in this process are going to be an orthogonal basis for the first k vectors that we started with. And this process is what is called the Gram-Schmidt process. So we'll try some practice examples with this process.